Hello viewers, Wagadaruna taking you through the story of A-level physics paper 2. And this video we are going to go through the topic of magnetism and alternating current, and in particular electromagnetic induction. So this video is suitable for students in both senior 5 and senior 6 offering physics as part of their combination. So this is what we hope to upload under this topic. So what is ticked means is already available on the platform, and what is not yet ticked means will be uploaded with time. And like I've already told you, here we're interested in the calculations, but complete notes are available in the books I recommend. So physics, there are 4 books, that is Physics Paper 1, Physics Paper 2, Topical Question Bank and its solutions. For mathematics, there are still Principal Mathematics, there are still 4 books, Math Paper 1, Math Paper 2, Termly past papers with marking guides, and Topical Question Bank. Subsidiary Math is only 1 book which contains both notes and past papers. So for any of the copies, contact the author on this contact. So before we start electromagnetic induction, there are 2 terms we need to know. One of them is called magnetic flux, and the other one is magnetic flux linkage. So magnetic flux is simply the product of the magnitude of the magnetic flux density and the area perpendicular to the magnetic field. We are saying area perpendicular because sometimes the field and the may be at an angle. To the horizontal. So that's why we say area perpendicular to the field. Or you can say magnetic flux, the product of the magnetic flux density and the projection of the area normal to the magnetic field. So magnetic flux is given by the symbol this, and its SI unit is Weber. In short, you write capital W and small b. So magnetic flux unit is Weber. So a Weber is the flux linking a circuit when the induced e.m.f is 1 volt and the flux is reduced uniformly to 0 in 1 second. So this word induced e.m.f, actually it is the main word when we talk about electromagnetic induction. So we are going to first reserve it and to come in when we talk about electromagnetic induction. That will be still in this video. That is where we shall see why we still say that it is reduced to 0 in 1 second. So for now, just know the definition, but the actual meaning will come when we deal with electromagnetic induction. So let us consider a coil of area A positioned in a uniform magnetic field of flux density B, such that the normal to its plane makes an angle theta with the magnetic field. So that is a coil, and the magnetic field is that in that direction. This will be the normal to the plane of the coil. So the component of B at right angles to the plane of the coil is B cos theta, because we said area and the field perpendicular to the area. So when I bring this on this side, I think remember where the angle lies is what becomes cos. So when I resolve this B to this normal, it becomes B cos theta, which is this. Then when I multiply, I'll come up with A B cos theta. I want you to be keen. Cos theta now, because previously we have been using theta as, for example, it was under the video of force on a current carrying conductor. The theta was between the field and the conductor. Okay, but this time around it is different. The theta is between the field and the normal to the plane. Field and the normal to the plane. So remember that. So if the magnetic flux is perpendicular to the area, then the flux through the area is given by AB cos 0 degrees. I think you remember you see something here. They said perpendicular, but the angle is 0 because the angle now is between the field and the normal. Field and the normal. So that means that B will be equal to magnetic flux over area. So from this formula, you realize that we can also define magnetic flux density. So what does that mean? It means that magnetic flux density can be defined in a number of ways. The very first definition we wrote, I think you remember it was coming from F equal to BIL, where I make B the subject and we can define. The second one was from F equal to B to V, where I make B the subject and you can define it. Now the third one is coming from flux equal to AB, where I make B the subject. So there are a number of definitions of ways of defining magnetic flux density. Now from this one of B equal to phi over area, we can define magnetic flux density as the flux threading. Threading means linking. We're going to look at it in the second definition, which is magnetic flux linkage. So is the flux threading an area of 1 meter squared, which is perpendicular to the magnetic field. Flux threading an area of 1 meter squared, which is perpendicular to the magnetic field. That means that we have another SI unit of magnetic flux density, which is Weber per meter squared. So one can say Tesla or Weber per meter squared. Both are correct SI units of flux density. So if a coil has more than 1 turn, then the flux through the whole coil is the sum of the fluxes through the individual turn, and this is what we call magnetic flux linkage. So these are the two definitions I wanted us to first know before we go to electromagnetic induction, because they will be very vital: magnetic flux and magnetic flux linkage. So the difference is simple. One, magnetic flux is for only 1 turn of a coil. Magnetic flux linkage is for all the turns of the coil. All the turns of the coil. That means that magnetic flux linkage is equal to number of turns multiplied by magnetic flux. And you already know that magnetic flux is AB cos theta. But remember, I want you to be so conscious of this theta. Because why am I saying that? Because previously, this theta has been the angle between the field and the plane of the coil, of the conductor. But in this particular case, theta is the angle between the field and the normal. Theta is the angle between the field and the normal. So something changes a little. I want you to be cautious about that. So where n is the number of turns of the coil. If the magnetic field is perpendicular to the coil of area A and n turns, it implies that magnetic flux linkage is NAB. So now we can define magnetic flux linkage as the product of the magnetic flux density and the area it links perpendicularly. So with that, we shall go through some questions. Question 1 came from U.A.C.E 1995, paper 2, question 5D, and it says, a coil of cross-section area 1.6 exponent negative 3 meters squared is to be used to produce a uniform magnetic flux density of 1.5 exponent negative 3 Tesla. Calculate the total flux through the coil. Total flux through the coil. So here we are given the cross-section area and the flux density, meaning that magnetic flux will be AB, area flux density, to come up with this Weber. Then question 2 says, a flat coil having an area of 8 centimeters squared and 60 turns lies perpendicular to the magnetic field of 0.4 Tesla. Determine Roman 1 the initial flux through the coil. Then Roman 2 the initial flux linkage. So I think by now you know the difference. Flux means 1 turn and flux linkage means all the turns of the coil. So initial flux will just be AB, area flux density. Then initial flux linkage will now be N times flux, which is this times this flux to give you this flux linkage. Question 3 came from U.A.C.E of 1994, paper 2, question 5F Roman 2, and says, a current of 1 ampere flows in a long solenoid of 1000 turns per meter. Okay, if the solenoid has a mean diameter of 8 centimeters, find the magnetic flux linkage with a 1 meter length of the solenoid. So first you need to get the number of turns, because they said 1000 turns per meter and the length is 1 meter, so total number of turns is 1000. Then the cross-section area, or the area of the plane, or the cross-section area of that coil, it will be pi d squared over 4. We are using over 4 because we are using here diameter. If this was radius, we would have said pi r squared. Then you convert this diameter to meters to come up with this. Then we know that B is mu small n I. I think you remember that under the subtopic of Biot-Savart law. So mu is the permeability of free space times the number of turns per meter times the current to give you this. So now that I have number of turns, I have area, I have B, I can now get magnetic flux linkage. So substitute for number of turns, area, then flux density to come up with this as the flux linkage they wanted. Then question 4 says a current of 1.620 ampere flows in a long solenoid of 10 to the power 3 turns per meter and diameter of 5 centimeters. Find the magnetic flux linkage for a 1 meter length of the solenoid. So some are the same as previous. Here I've chosen to first get radius, then I can get number of turns and the area. Then magnetic flux density, after which I can now multiply to get magnetic flux linkage. So same as the previous question. Okay, so now we have understood the two terms, magnetic flux and magnetic flux linkage. So when you know those two terms, you can understand what we call electromagnetic induction, because it all revolves around magnetic flux linkage. So what is electromagnetic induction? So this is a phenomenon by which an EMF is induced when flux linked to a conductor changes or when flux is cut. So those are the two words we shall be using. We can say flux linkage is changing or flux is being cut at a certain rate. And when this happens, when the flux linkage changes or when flux is being cut, the EMF has to be induced. Now I think you remember in the definition for a Weber, we talked about induced EMF reducing to zero. Why? Because when the flux stops to change, EMF is no longer induced, and that is how it can reduce to zero. So let us see an illustration. So we shall consider a wire XY connected in series with a galvanometer. I think you know the parts of the galvanometer. We have already made a video on moving coil galvanometer. So, and the purpose is to measure small currents. It is sensitive at measuring small currents. So when I connect this wire to a ballistic galvanometer and then place it between pole pieces of a strong permanent magnet, such that the plane of the wire is perpendicular to the field, as shown below. So you shall come and draw the poles of the magnet. So there will be a magnetic field due to those poles running from north to south. Okay, now when I come and put a wire here and I connect it to a galvanometer, initially there's no deflection. There's no deflection on the galvanometer, meaning that no current is flowing. Why? Because it is stationary. And here we say EMF is induced only when flux linkage changes or when flux is being cut. Those two words are the same. But something funny will happen. Do you know what I will do? If I get this wire and I move it up and down into this field, it means that I'm changing the flux linking this wire. Or it means that the wire is cutting the flux. Those words are the same, but I prefer this word of linking. I prefer the word of change in flux linkage. So when I move the wire up and down, the flux linking the wire keeps on changing. Now because it keeps on changing, even an EMF will be induced. And when an EMF is induced, it means that a current has to flow. That current which flows is what we call induced current. Induced current. I don't know if it is clear. So in short, each time a magnetic flux linkage changes, an EMF has to be induced. And when an EMF is induced, a current has to be induced also. So now with that we can write the following. 1 is that when the wire placed between the poles of a magnet is moved up and down between the poles of a magnet, the magnetic flux linking it changes, and as a result an EMF is induced in it. That is very vital. 2. Since the wire is connected to the galvanometer, a deflection is observed on the galvanometer. So a galvanometer is there to help us prove that current is really flowing, because current is invisible. Third point, when the wire is moved up, the direction of the induced EMF is opposite to that when the wire, so this is why not such coil, opposite to that when the wire is moved down. So if a deflection goes this side when the wire is moved up, it will now come this side when the wire is moved down. That's what they mean. When the wire is moved up and down faster, what does it mean? In the magnetic field, it means that the rate of change of the magnetic flux linking the wire increases. And when it increases, it means that induced EMF also increases. So this induced EMF depends on the rate of change of magnetic flux linking the wire. Induced EMF depends on the rate of change. How fast is the magnetic flux linking the wire changing? And the last bullet, when the wire is held stationarily between the poles of the magnet, okay, no EMF, know this word, no EMF is induced, implying that no deflection will be seen on the galvanometer. So an EMF is induced only when there is a change in the magnetic flux linking that conductor. That was an introduction. Now we shall go to the laws which govern electromagnetic induction. They are mainly two laws. One is called Faraday's law. So what does it state? This law states that the magnitude of EMF induced in a circuit, you can say circuit or conductor, in a circuit is directly proportional to the rate of change of the magnetic flux linked with the circuit. So this is what we have been saying. When you move it faster, then the EMF is bigger. When you move it up and down slowly, then the EMF is smaller. That is called Faraday's law. What about the second law? The second law is called Lenz's law. This law states that the direction of the induced EMF is such as to oppose the change causing it. Such as to oppose the change causing it. So these two laws can be written mathematically in this way. We shall say first, magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. And you know that magnetic flux is phi, so the phi dt means rate of change of magnetic flux. And induced EMF is denoted by E. When I put an equal sign here, I should bring a constant of proportionality, which is K. Now, why have we put the negative? The negative has been put to cater for the second law, because this one was catering for this first law, EMF being proportional to the rate of change. Now, when I bring in the negative, it caters for the second law because it opposes the direction of the change. It opposes the change causing it. But let's talk about it more, why the negative, the verse of the negative. So K is a positive constant, but the negative sign means that the induced EMF is in such a direction that if the circuit is complete, the current opposes the change in flux. Current opposes the change in flux. So that is in accordance with Lenz's law. Now from the definition, K will be equal to 1, meaning that E is equal to negative d phi dt. Negative d phi dt. Now, if the coil has n turns, the EMF induced will be given by E equal to negative n d phi dt. But we know that phi is equal to, or flux is equal to AB. So I'll come and substitute for AB. Now, why have I put A this side? It is because A is a constant, so I can pull it out of the derivative. And I remain with dB dt. So that implies that induced EMF will be equal to change in flux linkage over time taken. Now, this is the formula you're going to first use to calculate induced EMF. So, question 1. A flat coil of area 8 centimeters squared and 60 turns lies perpendicular to a magnetic flux, a magnetic field of 0.4 Tesla. If the flux is steadily reduced to 0 in 0.25 seconds, calculate the EMF induced in the coil. So you have to get the initial and the final. So initial is NAB, because they said perpendicular, which is this. Then the final is 0. So that means that induced EMF will be change in flux linkage over time taken, and change will be initial minus final over time taken to give you this, and that is the answer they wanted. Then question 2, a coil of 20 turns having an area of 0.1 meter squared is placed in a magnetic field of flux density 0.2 Tesla, so that the flux links the turns normally. Calculate the average induced EMF if the coil is completely removed from the field in 0.75 seconds. Completely removed means it reduces to 0. So initial magnetic flux linkage will be given by NAB to give you 0.4 Weber. Then the final will be 0 because it is completely reduced to removed out of the field. Therefore, induced EMF will now be change over time taken. Change over time taken, which is that. Okay. Then question 3, part A. A narrow coil of 10 turns and cross-section area 4 exponent negative 2 meters squared is placed in a uniform magnetic field of flux density 1 exponent negative 2 Tesla, so that the flux links to the turns normally. Calculate the average induced EMF of the coil if it is completely removed from the field in 0.5 seconds. Let us first begin with that. Completely removed, so initial will be that, and final is 0. Therefore, induced EMF will be change in flux linkage. Change in flux linkage over time taken, and that will be the induced EMF they wanted. Then Roman 2, so part B, let me see part B. It says, if the same coil is rotated about an axis through its middle so that it turns through 60 degrees in 0.2 seconds in the field, now it is not removed, it is within the field, calculate the average induced EMF. So turned through 60 degrees. So yeah, the initial flux linkage is this, we already know that, which was here. But the final is when it is turned through 60 degrees. So that angle will now be between the normal and the field, 60 degrees. That's why we are using it here to give you the final. Therefore, the induced EMF will now be equal to the change, this minus this, over the time taken. And that's what they wanted. So question 4 came from U.A.C.E 2001, paper 2, question 6b, and it says, a coil of 100 tons and cross-section area 0.2 meters squared is with its plane perpendicular to a horizontal magnetic field of flux density 1 exponent negative 2 Tesla. The coil is rotated about a vertical axis so that it turns through 60 degrees in 2 seconds. Calculate Roman 1 initial flux linkage through the coil and Roman 2 EMF induced in the coil. So initial flux linkage is NAB, which is this. Then final is when it is rotated through an angle of 60 degrees to give you that. Then the EMF will now be changed in flux linkage over time taken to give you that. And that's what they wanted. Then question 5 came from U.A.C.E 2005, part 2, question 6b, and says, a coil over 100 tons is wound round the middle of a long solenoid of 500 tons per meter and radius 8 centimeters. A sinusoidal current I equal to 10 sine 120 pi t amperes is passed through the solenoid winding. Find the amplitude of the EMF induced across the terminals of the coil. So 1 is flux density of the solenoid. Along the axis is mu and I. So substitute this a constant, number of times per meter, current, which is given by that. So the BDT, when I differentiate, this with respect to t, we learned that in pure math. So this is the constant. Differentiate sign, you get, first of all, differentiate this angle. 120 pi t, you get 120 pi, which is this. Then this one now, differentiate sign, you get cos, and you maintain the angle. So when you simplify this, you come up with this as your dB dt. So the magnitude of EMF induced is NA dB dt. I think you remember this formula, NA dB dt. So you shall substitute, N is here, area is here, and dB dt. So N is 100, area is pi r squared, then dB dt is this. We don't know the value of t, so you leave it there. So simplifying gives you this. But the said amplitude, now amplitude is this one, coefficient of this trig function. So amplitude will be that. So now I believe you are well versed with the introduction part of induced EMF. There should be a change in magnetic flux linking it. Okay, so now we shall go to what we call EMF induced in a moving straight conductor placed in a magnetic field. So consider a smooth conducting rod P2 of length L, which is free to move with a uniform velocity v over a smooth rectangular conducting flame placed in a magnetic field of flux density B. So there's a conducting rod P2, and this is the flame. the length is L, and the magnetic flux density is into the paper. So suppose P2 is moved to the right by a force Fa with a uniform velocity v. So if I get this one and I move it, do you know what will happen? There will be a change in magnetic flux linkage, or we can say magnetic flux is being cut. So let's put that force there. And we all know that when there is a change in magnetic flux, EMF has to be induced in the coil, and therefore current has to flow. So an EMF is induced in P2 due to the flux linking it changing. And because of that, current will flow as shown. So that will be the current flowing. Because it flows here, it will also flow in this flame. When it flows, now something will happen. According to Fleming's left-hand rule, whenever there is current and a magnetic flux or a magnetic field, there should also be a force whose direction is determined by Fleming's left-hand rule. So that force, if you call it FB, it will now act to the left according to Fleming's left-hand rule. And remember that force is equal to BIL. Now, since the rod is not accelerating, now why are we saying not accelerating? It is because we said it is pulled at a constant velocity. Each time velocity is constant, acceleration is 0. Where do we get it from? We get it from the first equation of motion, V equal to U.A.T. When this is equal to this, it implies that A.T is 0, meaning that A will be 0. That means that FA is equal to FB. Therefore, FA is also equal to BIL. Now, from the principle of conservation of energy, electrical energy generated per second is equal to the work done per second by force on moving P2. So electrical energy generated is power, which is EI, where E is the EMF and I is the current, is equal to power is also power, or work done is force times velocity. Why? Because acceleration is constant. So when I substitute for FA, I'll come and get BILV. Then the good thing, I is common, so I can still cancel it to get BLV. So this is the expression for EMF induced in a moving conductor, BLV, where V is the drift velocity, or the velocity in which the conductor is moving. So E is the induced EMF. So previously we have seen that induced EMF is change in flux linking over time. Okay, that formula we have used it. Now we want to use this formula, B equal to LV. So I is equal to E over R. You should remember that. So if they give you resistance and induced EMF, you can get I. But we know that E is this, so substitute, you come up with that. So magnetic force FB opposes the motion of the rod. Therefore, F is equal to BIL. I is here, L is here. So when I substitute, I'll come up with B squared L squared V over R. We are trying to get different formulas. So we already know that F is equal to BIL, and also F, if you're not given current, you should remember that current is this, so I can substitute to get still the F. Therefore, power developed is FB times velocity. FB times velocity, which gives you this, like that. But the key word is you remembering that EMF is BIL. BLV. So if the conductor is inclined at an angle theta to the field, it implies that E is equal to BLV sine theta, not cos, sine theta. Okay. So if the conductor moves with a velocity v at right angles to the field B, then so do electrons in it. So that means that force on each electron inside the conductor will be BeV, and the drift velocity of each electron will still be v, the same velocity with which the conductor is moving. By the summit, we can be given as I over NAE, where N is number of electron density, that is electrons per unit volume. Then EMF induced will also be still the same, induced on moving electrons. So the EMF induced on moving electrons is the same EMF induced on the moving conductor. So with that, shall go through these questions. Question 1 came from U.A.C.E 2012, paper 2, question 6C, and says, in figure below, a conducting rod P2 of length 20 millimeters rests on a smooth conducting frame to form a complete circuit of resistance 4 ohm. When a force F is applied, the rod moves at a constant velocity, note this word constant velocity, of 6 meters per second, perpendicular to a uniform magnetic field of flux density 1.5 Tesla. Roman 1. Explain why the rod P2 moves with constant velocity. So here shows that as the rod P2 is moved, it accelerates initially to the right and cuts the magnetic flux, causing an EMF to be induced. So each time the magnetic flux is cut, EMF is induced, or each time the magnetic flux linkage is changing, EMF is induced. Those two words are the same, they shouldn't confuse you. So since the circuit is a complete loop, an induced current flows along the rod. By Fleming's left-hand rule, magnetic force acts on the rod in such a way as to oppose the motion. Okay. With increased acceleration along the smooth conductor, a bigger EMF and a larger induced current flows, causing an increase in the magnetic force until it equals the applied force. So in this case, when the forces are equal, it means that acceleration is constant, and therefore velocity has to be constant. So basically that's why it moves with constant velocity, because opposite forces are equal. Then 2, calculate the magnitude of the induced EMF. And 3, calculate the magnitude of the force. Okay. So magnitude of the induced EMF as it moves, it will be BLV. So B flux density, L is length, V is the drift velocity, which is that. Then magnitude of the force, we need to get the current. Current is E over R. E is here. R is given the question, you get current. Then after current, I can now say BIL. BIL to give you the force. And that's what they wanted. Then question 2 came from U.A.C.E 2014, paper 2, question 6C, and says, a single rectangular loop of wire with dimensions 35 centimeters by 75 centimeters is arranged such that part of it is inside a region of uniform magnetic field of flux density 0.545 Tesla, and part of it is outside the field. The total resistance of the loop is 0.23 ohm. Calculate the force required to pull the loop from the field at a constant velocity of 3.4 meters per second perpendicular to the field. Okay, so EMF induced on the loop when pulling it out of the field is given by BLV, so flux density, length, velocity, which gives you that. Then current in the loop is E over R, is here, R is given the question, which is that. Therefore, so let F be the force required to pull the loop from the field. So mechanical power developed is equal to electrical energy developed. Fv is equal to EI. I think you know this. F is the force required, V is the velocity, EMF current. Then make F the subject, and that's what they wanted. Question 3 came from U.A.C.E 2009 paper 2 question 5b and says a straight wire of length 20 centimeters and resistance 0.25 ohm lies at right angles to a magnetic field of flux density 0.4 Tesla. The wire moves when a PD of 2 volt is applied across its ends. Calculate Roman 1 the initial force on the wire, Roman 2 the force on the wire when it moves at a speed of 15 meters per second, and Roman 3 the maximum speed attained by the wire. So Roman 1 initial force is BIL, I is PD applied over resistance, so substitute B, PD applied resistance, and length to give you this. Then the force on the wire when it moves at a speed of 15 meters per second. So their induced EMF will be BLV, which is this. Therefore current will now be V applied minus induced EMF, because they oppose each other, over R to give you this, which gives you in the end that. So induced EMF always opposes the change causing it, that's why it's subtracting. So F will now be BIL, but this time I has changed to this, and that is it. Then Roman 3, the maximum speed attained by the wire is BLV max. So maximum speed means that induced EMF is exactly equal to the applied PD. Applied voltage is that, induced EMF is this, so we can get the maximum speed. And that's what they wanted. Then question 4 came from U.A.C.E of November 1998 part 2 question 6b and says a metal rod XY of mass 0.2 kilograms, length 0.8 meters, and negligible resistance rolls down frictionless metal rails PP prime and QQ prime, inclined at 30 degrees to the horizontal. The rails lie in a uniform vertical magnetic field of flux density 0.4 Tesla. The ends PQ of the rails are connected to a resistance of 5 ohms as shown in the figure above. Calculate the constant speed the rod attains. Okay. So at constant speed it means acceleration is 0. So let's draw it, viewing it from the sideways. There is a conductor, it has a weight, then component of the weight part of the plane, and perpendicular to the plane is that. Because of this there will be normal reaction, which is R. Then the field is in that direction, meaning that when there is this field, magnetic force will be in this direction, because we know the current is because we know the direction of the current. Then resolving that force, parallel to the plane is this, and perpendicular to the plane is this. So at equilibrium, it means that for acceleration B0, it means that forces up the plane are equal to forces down the plane. That's why we are equating the two. But we know that F is BIL. Then come and substitute for M, for G, for theta, B, I we don't know, L, theta. So I is the only unknown, meaning I can get the value of I as that. Then induced EMF is BLV and E is IR. That means that V, I can make V the subject to give me the velocity I want. So that has been induced EMF induced in a moving conductor, moving straight conductor. What about EMF induced in a rotating coil? EMF induced in a rotating coil. So consider a rectangular coil of n turns and area A being rotated at a constant angular velocity of omega in a uniform magnetic field of flux density B about an axis perpendicular to the field. That will be the coil. We are viewing it from, should I say, upward or sideways? So this coil is rotating in this direction. But in actual sense, it's like this, whereby you see this, it is rotating like this, isn't it? So now for us, we are seeing only this top part, this one. That is the only part we are seeing. So we're interested in the angle to the normal, which is theta. So flux linking the whole coil is given by n times phi, which gives you BAN cos theta. But remember, the theta is the angle between the field and the normal. Okay, and we know that angular velocity is rate of change in the angle, okay, which is theta over t. Therefore, when I make theta the subject, will come up with omega t. Therefore, when I substitute for theta, I'll come up with this expression. So wherever there is a change in flux linking the coil or circuit, an EMF has been induced. That is what we have always been saying about electromagnetic induction. So induced EMF is given by this. I think you remember that. Come and substitute for phi. It is AB cos omega t. A can come up with the derivative because it's a constant. So when I differentiate this, I'll come up with B. When I differentiate this, I'll come up with B omega sine omega. This one. But there's also this one. And there's a the negative goes because when I differentiate cos, I get the negative. So negative here with this negative gives a positive. That's why you're not seeing a negative here. So this is the expression for EMF induced in a rotating coil. So there are different things. The first one of BLV was for a straight conductor moving in a magnetic field. Now this one is for a coil rotating in a magnetic field. So you shouldn't confuse them. So if sine omega t is equal to 1, it means that induced EMF is maximum. And to be maximum when t is equal to this. And this is what they call amplitude, the coefficient of a trig function. So E equal to this is the amplitude or peak value of the EMF induced in a coil. This maximizes the induced EMF in the coil when this is equal to 1 or when omega t is equal to 90 degrees. Thus, a coil rotating with a constant velocity in a uniform magnetic field produces a sinusoidal alternating EMF, Sinusoidal means keeps on changing. Keeps on changing. Like a sine wave. Sinusoidal comes from a sine wave. But we will understand this mainly when it comes to alternating current. Alternating current. Okay, so question 1 came from U.A.C.E 2010 paper 2 question 6c and says a rectangular coil of 50 turns is 15 centimeters wide and 30 centimeters long. If it rotates at a uniform rate of 2000 revolutions per minute about an axis parallel to its long side and at right angles in a uniform magnetic field of flux density 0.04 Tesla, find the peak value of the EMF induced in the coil. So maximum EMF is NAB omega, where A is length times width and omega is 2 pi f. So we are going to substitute. N is the number of turns, A is the area, this and this, but you convert to meters. Then B is the flux density, then 2 pi f. 2 pi f. F is the revolution per second, but this was per minute, so we have to change to per second. That's why you're seeing me dividing by 60. So in the end, you'll come up with that as the maximum EMF induced. Then question 2 came from U.A.C.E 2009 paper 2 question 6 and says a flat circular coil of 2000 turns, each of radius 50 centimeters, is rotated at a uniform rate of 600 revolutions per minute about its diameter at right angles to a uniform magnetic field, magnetic flux density 5 exponent negative 4 Tesla. Calculate the amplitude of the induced EMF. So amplitude is NAB omega and A is pi r squared, omega is 2 pi f. So come and substitute for N, for r squared, for B, and for the revolution per second to give you this as the amplitude. So amplitude is the same as maximum EMF induced. Question 3 came from U.A.C.E 1996 part 2 question 6b and says a coil of 100 turns and area 2 exponent negative 2 meters squared lies in a magnetic field of flux density 3 exponent negative 3 Tesla and rotates uniformly at 100 revolutions per second about an axis perpendicular to the magnetic field. Calculate Roman 1 EMF induced when the plane of the coil makes an angle of 60 degrees with B. Plane, not that word. Plane of the coil is the one making an angle of 60 degrees. But remember, in our formula, we are interested in the angle between the normal to the plane and the field. So should begin with that. Then Roman 2, amplitude of the induced EMF. So here we're making a sketch to see where the angle is. So this is the 60 they have given us, but the angle we are using is between the normal and the field, so it will be 30. So don't make a mistake. So in this EMF is this, which is the same as that, because omega t is the same as theta. So I'll substitute now N A B 2 pi f and sine theta, which is that. Roman 2 amplitude is NAB omega, which is that. Then question 4, a rectangular coil of 100 turns and area 400 centimeters squared is rotated about a horizontal axis at a constant rate of 50 revolutions per second in a horizontal magnetic field of 0.21 Tesla to the axis. Calculate Roman 1 maximum induced EMF and 2 induced EMF when the coil is 30 degrees with the horizontal. So still the same story. Maximum is NAB omega, which is that. Then for Roman 2, it is the same thing. 30 here there will be 60 to give you that. And that's what they wanted. So now we shall go to EMF induced in a rotating disc. The other one was a rotating coil. Now this is a rotating disc. Others call it Faraday's disc, or others call it homopolar generator. Whatever they call it is the same thing. So it consists of a copper disc which is rotated between the poles of a magnet. The magnetic field is perpendicular to the plane of the disc and parallel to its axis of rotation. So you have a disc, center, that is the radius, then it is rotated in that direction in presence of the magnetic field. So connections are made to the axle, which is the center, and the rim. So center is called axle, circumference is called the rim. It is assumed that the magnetic field is uniform over the radius CD. So consider a disk of radius r rotating in a field of flux density B with an angular velocity omega. The radius CD sweeps out the area of the disk when it rotates. Therefore, the magnetic flux linked with the disk will be given by AB, where is the area of the disk, and EMF induced between the rim and the center of the disk, because the radius continuously cuts the magnetic flux, and EMF is induced. So we know that E is equal to negative d phi dt. So come and substitute. Phi is AB. Phi is AB, but this time it is the radius which is continuously cutting. That's why we are saying dA dt, and B is constant because they said uniform magnetic flux. So the ADT is the same as area over for one revolution over area being swept. When the whole of this area is swept, it means area of is the same as area of a circle, and the time is capital T, where T is period, and we already know that period is given by 2 pi over omega. So come and substitute. Substitute here, we have negative B, we have area, we have this, the ADT is this one, so substitute 2 pi r squared, pi r squared is here, divide by capital T, which is pi over omega, which is here. So simplify. When I put a multiplication sign, I get the reciprocal. So reciprocal, I'll come up with this expression. Then pi will cancel, and I'll come up with negative a half br squared omega. So magnitude means you ignore the negative and you remain with only this. So that is the expression for induced EMF for a rotating disk, where r is the radius of the disk. Also, you know that omega is 2 pi f. You should remember that. So I can substitute for omega to give me this as the second expression for induced EMF. So what we need to note is that if the disk has a radius r1 and the axle at the center has a radius r2, the area swept out by the rotating radius of the metal disc will be this. Now it is for example, what they are meaning is that if here there is some hollow part axle, so the area being swept out is this one. That's why you have to subtract. Therefore, EMF now becomes this. Then if the angular velocity is constant, then the induced EMF is also constant. So if the rate of rotation is constant, then EMF induced is also constant. So with that, we can go through some questions. Question 1. A circular metal disc of area this is rotated at 50 revolutions per second about an axle through its center and perpendicular to its plane. The disc is in a uniform magnetic field of flux density this in the direction of the axle. Calculate the EMF induced in the disc. So we know that B is equal to E is equal to B pi r squared F. Pi r squared is area, so because it's already given, that's why you're using area, so I come and substitute B area F. F is revolutions per second to give you the EMF induced. Then question 2 came from U.A.C.E 2011 paper 2, question 7b, Roman 2, and says a copper disc of radius 10 centimeters is placed in a uniform magnetic field of flux density 0.02 Tesla with its plane perpendicular to the field. If the disc is rotated parallel to the field about an axis through its center at a revolution at 3000 revolutions per minute, calculate the EMF that is generated between its rim and the center. So E is equal to given by this, so substitute and get the EMF. Question 3 came from U.A.C.E 2018 paper 2, question 5c, and says a conducting disc of radius this with its plane perpendicular to a uniform magnetic field of flux density this rotates at 15 revolutions per second about an axis through its center and perpendicular to its plane. Calculate Roman 1 the magnetic flux threading the disc at any time. Roman 2 the EMF generated between the center of the disc and any point on its rim. So flux is that, area is pi r squared, substitute flux density, you get the flux. Then Roman 2, the one the EMF generated, which is B pi r squared F, substitute and get the answer. Then question 4 came from U.A.C.E 1995 part 2, question 6b, Roman 2, and says a circular aluminium disc of radius 30 centimeters is mounted inside a long solenoid of 2 exponent 3 turns per meter carrying a current of 20 amps such that its axis coincides with that of the solenoid. If the disc is rotated about its axis at 40 revolutions per minute, what will be the EMF induced? So here we shall come out for the solenoid, you shall get the magnetic flux density, after which you can now get the induced EMF from B pi r squared F, which gives you this, and that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded that this video will be on ballistic